The spark of an idea. It all starts with a spark, doesn't it? Just like the electricity that powers our world. Hello science fans, are you ready to explore the amazing world of electricity? Bill Nye here, ready to electrify your understanding of circuits. Today we're diving into the electrifying world of circuits. We're going to unravel the mysteries behind how these pathways of power work. Electricity is like water flowing through pipes. It needs a path to follow and something to push it along. But instead of water, we're talking about electrons moving through wires. These tiny particles are the key to everything we're discussing today. This flow of electrons is called electric current. It's the lifeblood of our electronic devices. It powers everything from lights, illuminating our homes and streets, to computers, the complex machines that run our modern world. A circuit is the path electricity follows. It's the roadmap for electrons. It needs to be a closed loop, like a racetrack for electrons, so they can keep moving continuously. For a circuit to work, it needs a power source, something to get those electrons moving, like a battery, to push electrons along the wire, providing the energy they need to do their job. If the path breaks, the current stops, the flow is interrupted. No flow, no power. It's as simple as that. We can add different components to the circuit, each with its own unique function, to control the flow in amazing ways, shaping the electricity to do exactly what we want it to do. By combining these components in clever and intricate designs, engineers build everything from flashlights, simple devices that bring light to the darkness, to supercomputers, the pinnacle of computational power. Today we'll explore a special circuit, one that's particularly fascinating and useful. That's key to tuning radios and filtering signals, allowing us to communicate and access information. It's called the RLC circuit, named after its three main components. And it's fundamental to modern technology, playing a crucial role in countless devices. We'll see how three components, the stars of our show today, resistor, inductor, each with its own unique properties, and capacitor, the energy storage expert, work together in a scientific dance, creating a circuit that's more than the sum of its parts. By the end, you'll see how powerful this combination can be and how it shapes the world around us. Let's get started. It's time to unlock the secrets of the RLC circuit. Section 2. Meet the RLC circuit, the Big Three. These three components form the cornerstone of countless electronic devices and systems. Understanding their roles and how they interact is fundamental to grasping the behavior of many circuits. What's an RLC circuit? The name says it all. It's a circuit composed of three essential components: a resistor, an inductor, and a capacitor. These aren't just any components. They're the fundamental building blocks that allow us to manipulate and control electrical signals in a myriad of ways. R for resistor, the workhorse of the circuit. It opposes the flow of current, dissipating electrical energy as heat. Think of it as a valve controlling the flow of water in a pipe. L for inductor, a coil that stores energy in a magnetic field when current flows through it. It resists changes in current, acting like a flywheel that smooths out the flow. And C for capacitor. This component stores energy in an electric field, acting like a small rechargeable battery. It opposes changes in voltage, smoothing out voltage fluctuations. Connect these three with a power source, carefully placing each component in its designated spot, and you've got an RLC circuit, a fundamental circuit configuration with a wide range of applications. Each component has a unique job, a specific role to play in the overall behavior of the circuit. The resistor controls the pace, limiting the current and preventing overloads. It's the steady hand that keeps everything in check. The capacitor stores energy, ready to release it when needed, providing a boost or smoothing out dips in the power supply. And the inductor keeps the flow steady. It resists sudden changes in current, preventing spikes and ensuring a smooth, consistent flow of electricity. Together, they can do things none could do alone. Their combined effect creates a dynamic system capable of complex behaviors. You can connect them in series, one after another, creating a single path for the current to flow through. Or in parallel, giving electricity multiple paths. This allows the current to divide and flow through each component simultaneously. Each arrangement changes how the circuit behaves, influencing its response to different frequencies and signals, giving engineers options. These different configurations allow for fine-tuning and optimization for specific applications, but their fundamental roles stay the same. They're the building blocks of electrical control. The resistor still controls current, the capacitor still stores energy, and the inductor still resists changes in current. The real magic happens with alternating current, or AC, a type of current that changes direction periodically. like what comes from your wall outlet. This alternating current is what powers most of our homes and businesses. With AC, electricity flows back and forth rapidly. This constant change in direction creates a dynamic environment within the circuit. This is where the capacitor and inductor really shine, exhibiting their unique properties of reactance, responding to the changing current in unique ways. The capacitor opposes changes in voltage, while the inductor opposes changes in current, creating a complex interplay of forces. Their interaction lets RLC circuits tune into specific frequencies. This is the principle behind radio receivers and many other communication devices. It's a dynamic dance of electricity, a constant push and pull between the components, creating a fascinating and complex system happening all around you. From your smartphone to your car, RLC circuits are at work. RLC circuits are everywhere, performing a wide variety of tasks, quietly making technology work. They are the unsung heroes of the modern world. Let's meet each team member up close. We'll examine their individual characteristics and how they contribute to the overall function of the RLC circuit. Ready? Let's dive in and explore the fascinating world of resistors, inductors, and capacitors. Section 3, the resistor or R, the slowdown crew. First up, the resistor. Its job? Resist the flow of electricity. Imagine running through water versus air. The resistor slows electrons down, just like water slows you. This resistance turns some electrical energy into heat. Ever felt a warm device? Thank resistors. Resistance is measured in ohms. More ohms means more resistance. Engineers use resistors to control current and protect sensitive parts. Without them, circuits could overload and break. Resistors are everywhere. Small, color-banded cylinders in almost every device. The color bands tell you their resistance value. By choosing the right resistor, engineers fine-tune how much current flows. In an RLC circuit, the resistor's job is to dissipate energy as heat. It provides a damping effect, like shock absorbers on a car, making the circuit stable. The resistor tames the energy, ensuring the circuit doesn't oscillate forever. It's the steady, reliable foundation of the team. Next up, the energy saver. Section 4. The capacitor or C, the energy saver. Meet the capacitor, the circuit's energy storage specialist. Think of it as a tiny, super-fast rechargeable battery. It stores energy by separating positive and negative charges on two plates. Capacitance, measured in farads, tells us how much charge it can store. In AC circuits, the capacitor constantly charges and discharges, letting high-frequency signals pass, while blocking low ones. This makes it perfect for filtering and smoothing voltage changes. In an RLC circuit, the capacitor is always charging and releasing energy, creating unique oscillations. It's like an energy piggy bank, helping shape the circuit's behavior. Now, let's meet the inductor. And now for our final team member, the inductor, represented by the letter L. The inductor resists changes in current, steady as she goes. It's usually a coil of wire. When current flows, it creates a magnetic field and stores energy there. Inductance, measured in henries, tells us how much energy it can store. When current changes, the inductor pushes back, opposing the change. It lets steady DC flow easily, but resists fast-changing AC. This makes it great for filtering out unwanted high-frequency signals. In an RLC circuit, the inductor stores and releases energy in a magnetic field, always interacting with the capacitor. The back and forth between capacitor and inductor is the heart of RLC circuits. Together, they create oscillations that are key to tuning and filtering. Let's see how they all work together. Now that we've met the team, the fundamental components that make up so many electronic circuits, the resistor, capacitor, and inductor, each with their unique properties and behaviors, let's see what happens when they all work together, forming a dynamic interplay of electrical energy. We're about to explore the fascinating world of RLC circuits. In an RLC circuit powered by an AC source, we'll observe how these components interact when subjected to alternating current. The AC source pushes current. It's the driving force behind the circuit's activity, constantly changing direction and magnitude. The inductor resists sudden changes, so current builds slowly. It opposes the rapid fluctuations in current, storing energy in its magnetic field as it does so. The capacitor charges up, storing energy, accumulating electrical charge on its plates, and creating an electric field, while the resistor turns some energy into heat. It dissipates electrical energy, converting it into thermal energy through the process of electrical resistance. As the AC reverses, changing its polarity and direction, the capacitor discharges, sending energy back through the inductor. It releases the stored electrical charge, creating a current flow in the opposite direction. The inductor stores this energy in its magnetic field, once again resisting the change in current direction, then releases it as the current changes again. This continuous exchange of energy forms the basis of oscillation. This creates a cycle, a repetitive pattern of energy transfer and transformation. Energy sloshes between capacitor and inductor, creating a continuous exchange of electrical potential and magnetic field energy, with the resistor damping the motion, gradually reducing the amplitude of the oscillations. This back and forth is called oscillation, a fundamental behavior in many physical and electrical systems, like a swing moving higher and lower, gradually losing momentum due to friction and air resistance. The resistor acts as a damper, similar to friction in a mechanical system, slowly bleeding off energy as heat. It's a crucial element in controlling the oscillations within the circuit. Without the resistor, oscillations would go on forever. The energy would continuously transfer between the capacitor and inductor without any loss. With it, they eventually settle down, reaching a state of equilibrium as the stored energy dissipates. The AC source keeps the cycle going, providing a continuous input of energy to sustain the oscillations. Just like pushing a swing, adding energy at the right moment to maintain its motion. This elegant energy exchange is what makes RLC circuits so useful, enabling a wide range of applications in electronics. Now, where do we find them? What are some practical examples of these circuits in action? You might be thinking, where do I see RLC circuits? The answer? Everywhere. They're key to tuning radios and TVs. When you turn the dial, you're adjusting an RLC circuit to pick out one frequency. The circuit acts as a filter, letting only your chosen station through. This principle is used in cell phones, Wi-Fi routers, and any device that selects specific frequencies. RLC circuits also split audio signals in high-quality sound systems, sending bass to woofers and treble to tweeters. They're used in oscillators, which create precise timing signals for computers. Power supplies use them to filter out electrical noise. From airport metal detectors to hospital equipment, RLC circuits are everywhere. They're the unsung heroes behind modern technology. Now let's talk about resonance. We've talked about tuning and a special frequency, resonance. Resonance is when the inductor and capacitor's effects cancel each other out at one frequency. At this resonant frequency, the circuit passes current most efficiently. The resistor is the only thing limiting the current at resonance. Energy sloshes back and forth between inductor and capacitor with maximum ease. It's like pushing a swing at just the right rhythm. You get the biggest motion with the least effort. This is how radios tune to one station and ignore the rest. RLC circuits can be designed for sharp resonance, responding strongly to one frequency and weakly to others. This lets us pack many signals into the airwaves without interference. Resonance is the secret to clear communication in our wireless world. It's not magic, it's science in action. Let's wrap up our journey. We've journeyed through the world of RLC circuits. We've met the resistor, capacitor, and inductor and seen their elegant teamwork. This simple trio is the foundation of modern electronics. RLC circuits control the flow of electrons to perform precise, useful tasks. They filter noise-tuned signals and make global communication possible. Even particle accelerators use giant RLC circuits to explore the universe. The same principles apply whether in your phone or a massive collider. Next time you tune a radio or connect to Wi-Fi, remember the science at play. R, L, and C, working in harmony, make our world possible. Science is everywhere waiting for you to discover it. Consider that.